what do you feel like crap about? Like, what do you not, what are you not comfortable in, or at least comfortable if you feel pretty good with everything? Like, what would you want to work on first? Is what I'm trying to ask.
Um, I would say some of the math problems
Mhm,
are a little confusing.
sure. Okay. Let's do how. Okay. How is number one on that page the law of conservation of energy? Okay, number one on both of these worksheets is the same problem. Uh, it's the same problem. And number two is a little bit harder. So I guess I would work on number two unless you wanted to start with a problem like number one on either worksheet.
Um, I don't know. I guess I'm fine with either.
Okay, so let's do it all then, is what it sounds like. So let's have it doesn't really matter, to be quite honest. Let me just review a little bit so that I can get it as close as possible to what you're actually doing. You got mountain guys, you got trucks. Okay, pretty standard stuff. Okay, I know what to do. I got it. All right, so we're gonna have, all right. Can you see what I'm writing?
Yes.
Great. So I'll make a problem and we will solve on top of a, doesn't matter, 50-meter hill. So can you do this? I mean, I'm pretty sure you can. I think you could do this if given enough time, but how, like looking at this right now, how comfortable do you feel to be able to solve? How fast is it moving at the bottom? It's at the bottom.
Um, this is the one with the, okay, so it's finding, I don't know, I think I can do it. I think I need to see an example
Of
first.
course, yeah, yeah. So I really want to drive home before I get into it that this is one type of problem that you're going to see on your test. You're going
Mhm.
to see this, and it is your equation is going to be P top KE bottom. And if you
Oh,
don't
okay.
see, yeah, and if you, this is number one on the law of conservation of energy worksheet, and this is also number one, whatever, conservation of energy worksheet,
Mhm.
where again, like I said here, it's at rest. So there's no initial kinetic energy. And then the second, this is where it starts. That's the initial. There's only potential energy. I'll definitely go through it and we'll draw a picture. But this is one of the problems you will see. And if you don't, it'll be a little more complicated than this, but it will be based on this. This is the second situation when, well, now it's at the bottom, right? Top, bottom. Now, guess
Mhm.
what? There's no kinetic energy. I'm sorry, at the bottom, there is no potential energy. PE equals 0. KE equals 0. So getting into it and drawing the picture, I want to go, hopefully didn't confuse you, but, oh, and you're also given two things usually. Here's a height and here's a mass.
Mhm.
If this is the equation, well, mgh, yeah, 1/2 mv squared. How many variables do I have? Here's 1, here's 2, here's 3, there's 1. 3 variables.
Mhm.
So, and I'm going into this because I could give you the exact same problem, and that's exactly what those differences in number one are. On the worksheet that's labeled conservation of energy, law of conservation of energy, you're given the mass, right, for us, and you're given the height.
Mhm.
Use your algebra and solve for V. The number one on the other worksheet, it's the same exact problem. Now you're given the mass, and now you're given the velocity at the bottom. Solve for h, use algebra, okay?
Mhm.
Okay. Please drive that home, because I mean, I'm going to go ahead and solve it for you, but it's really all the same, basically. Drive this equation
Yeah.
and solve for a variable. So
Okay.
talked about it. It starts here. You can draw a picture. It's 50. Don't care, right? It's at some height, and it has a mass. Again, I don't care, but I just care for the calculation. So sure, let's write it down. 50 meters. Okay. Now they're asking, how fast is this thing moving? So V equals question mark, like always. This is our
Mhm.
equation. Again, because there's no kinetic energy here at the top of its motion, because it's not moving. There's no potential energy here at the bottom, because it's on the ground. That's why we can use that. So again, we would have this. This would be our equation to solve for. And
Mhm.
we want to solve for V. And you know very well how to do that, I think, but let's do it. I'm going to go a little quicker. Let me know if you don't like this, and that's fine with me. I'm going to cross those m's out. I'll divide both sides by m. Well, guess what? They go away. I'll multiply both sides by 2. So now my equation will be 2gh equals v squared, as always, right?
Mhm.
Bam, and it's done. It's 2 times, you guys are using 9.8, right? So 19.6 times 50. Oh, I can actually do that. It's 98. Let's see, 2 times 9.8 times 50, or 980, my bad. And square root of 980. Great, it's moving. It's that range. Before it was like 24 meters per second, 27 meters per second. Cool, it's in the range. We did it right.
Mhm.
Notice I don't care about the mass. Did it show up in my last final equation? No. So if this
Mhm.
ball weighed 1,000 kilograms, if it was huge, conservation of energy tells us I don't care. That's the beauty of this equation here. And
Yeah.
you mastered this concept if you can do that, and then solve the problems like we're doing. It sounds like you're conceptually there, and it's just a little bit going into the problems, and hopefully this helps, because you're going to see this one, as I said before.
Okay.
Okay, so the next one, a little more complicated, but it's the exact same thing. Now you're just dealing with a little bit of extra energy. So let's say, okay, I'm gonna just give you this stuff because I think we're good on that. It weighs 25 kilograms, and it's sitting at a height of, let's say, 100 meters this time, on top of hill. Your standard problem. You see that? You see how little that information is, but immediately already you can solve for velocity. Drive that home.
Mhm.
So now we're going to say the ball generates some heat. As always, we've gone through this many times. Ignore air resistance. If it doesn't say anything about air resistance, you ignore it. But now we're going to say the ball creates, whatever the word is, creates, that's fine, creates thermal energy and sound. Sure. Now we're not ignoring, it doesn't matter why, but you're not ignoring this extra energy. That's all you need to know, is that there's extra energy because it's rolling down, touching the ground. Now the air's hitting it as it's going down. Great. And it creates, okay, I got to be careful so the numbers work out, I guess. Let's say 50, I guess. So there, the ball creates thermal sound energy. So the key here is that, okay, the words that you're seeing and you're going to see as it rolls down the hill. And then you see that and you're like, oh, that's a little weird. It doesn't make sense. How am I supposed to interpret this? Because it's gaining this energy all the way down. But to simplify your life, it's at the bottom.
Mhm.
You just add that. Oh, wait. So pretend I didn't do that, right? And what's the equation, right? PE bottom sorry, top equals KE bottom. Same situation. This is the initial situation. There's no kinetic energy. It is at rest.
Mhm.
This is 2. The second situation at the bottom of the hill. There's no potential energy because it's on the ground. Have to have height. Now we said this. I'm just trying to make it clear that this is the exact same situation as before, but now let's take that into account. And so what I was saying before is that as it rolls down the hill, you interpret that as at the end. So that's why when you see your equation, it's plus T plus S. And I hope that's clear for you. That's, I think, what you were using. Thermal plus
Yeah.
sound. Okay, cool. I could write thermal as you did. Doesn't matter, right? And so I know I've been saying it, but is it clear why it's over here? You know, I could write this PE top. It has to go on one side of the equation. It's either left or right, right? But
Mhm.
if it's over there, hopefully that's maybe not clear exactly why, but it just is not that way, at least. Okay.
Yeah, it kind of makes sense.
Yeah. Okay, cool. So then what do you do? Well, you solve the problem now. Just as before, where you say, oh yeah, I've been doing this my whole life now. It probably feels like for you, but MGH, that's potential energy. MGH, cool. What's kinetic energy? Of course. And then now you got to say, oh, plus T plus S, thermal plus sound. I don't care what you call it. You can call it whatever you want, but it's 50 joules, right?
Mhm.
And then I didn't give you a thing, let's solve for velocity, obviously, since we have mass and height. So we're given that. This is a number. We're given that. This is a number. We're given that number. Guess we have to solve for that.
Okay.
Anything at all? I'm going to redo that whole thing and just kind of go through it more directly as an example, like the exact steps you need to do. But that was kind of the more in-depth explanation, I guess.
Okay.
Any questions on that?
No, not so far.
Okay, let's solve for a different one. I don't want that. Sorry. I wanted to give you the different variable. I dropped some a cliff at the bottom. At the bottom, speed is, I don't know, let's say 22. Let's make it move pretty fast. Let's do like 56 meters per second. How tall is the cliff? So I read this and I say, dropping something from a cliff, an apple, don't care what it is, okay. At the bottom, they give me a speed, okay. Well, velocity is 56 meters per second. And I say, okay, then they want this. Well, that's weird. I'm missing information. Well, if you do see this, which you might, you say, okay, well, I know I always start here. I may have to add some thermal energy. I may have to otherwise do something else. I know it's that, and it makes sense because drops means no kinetic energy at the top. Left side of the equation is the top, is the initial. The bottom here is the right side. Oh, it's at the bottom of the cliff. No potential energy. Cool. This seems to work. Okay. Well, I'm given V and I have H. Okay. MGH equals 1/2 mv squared. And then I see, oh, right. I don't care about M. Mass doesn't matter. Or let's just solve for H because that's what you have. So, well, so H is apparently 1/2 mv squared. And you can see that they are canceled again here. So you don't need the mass. On your problems, they gave you the mass, but it's useless information because it doesn't matter. But he might, this is more of a standard one, and he might throw this on here basically to see if you really understand it, I guess. So, okay, hooray for us. I'm going to simplify here. Please stop me if you want, if you're not okay with that, but I think you are. And you say, oh, okay, well, 56 squared divided by 2, 9.8. Oh, well, isn't that nice? Okay, and do your thing. Does it make sense? Okay, it's moving pretty fast, a lot faster than normal. So I guess, okay, 160 sounds good to me. And the math, will trust your intuition and do all that. This is the basic one that you'll see. And so if we go again, you're going to see, again, the same problem, but he likes to give some extra energy, some thermal stuff. So let me write one just like it is here, because I know what you mean, how it's different. Because there's a lot of this Riddler's revenge thing is like, there's a lot of information here, and it can be hard to get. So let's see what I got. Okay. I don't know the actual numbers for this, but
If it's possible, after this one, can we do one where it talks about like percent? Like we did a practice one today, and he said it was definitely going to be on the test, and it was something like wait, let me see if I can find it. I wrote it down. 10%. It gave a mass and a height, and then it says, unfortunately, they lose 9% of potential energy down and thermal energy as on the hill. How fast will the person be traveling at the bottom of the hill?
So say it again. They give you mass and an H, and then you lose 90% potential to the thermal.
Yeah, 19% to the thermal.
Okay. Yeah. Okay. We kind of talked about this before, but this is good. This is a good one because it is same type of thing, right? And so it loses it as it rolls down the thing. Oh, she's not there anymore. Hey.
Hi.
Good. So, okay, 90% potential energy lost to thermal, and it's like rolling down the hill.
Yeah, so it's like how fast will the person be traveling at the bottom of the hill?
Okay, so it's this conservation of energy thing, 90% to thermal. Okay, so let's calculate. So I don't need anything. You go, this is how it is. So PE top, it starts at rest, I assume. It may not, but just more numbers to use.
I assume so because it just says rolls down a hill.
Yeah.
So yeah, okay. Probably rest.
And that's all you've seen on the thing. So on your problems that I've seen. So it makes sense. So here you go. Here's your equation, right? Your familiar equation that you know. The key here, the understanding, the insight, whatever you want to say, is that whatever number you calculate here, well, guess what? You're given it. Why? Because MGH, you're given a number. Let's call it 100. You cool with that? Okay. You sure?
Yeah.
Okay, cool. Then 100 joules, we're saying, equals the total energy at the bottom. Obviously, right? That's not so bad. But now it's saying that, now it's saying what? Well, 10% of that 100 joules goes to kinetic energy. Well, why? Because 90% goes to thermal and sound.
Mm-hmm.
And so that's the problem. Well, sorry. Okay. So you're going to be given a number here. Did they give you thermal and sound? Let me see. 1/2
No.
v squared. Okay, that's okay. I think we can still do it if it's just conceptual.
Oh, it just says 90% of his potential energy. He loses 90% of his potential energy to sound and thermal energy as he travels down the hill.
Okay, and there aren't even any numbers, are there?
No.
Okay, makes sense. So I'm going to go to the next one here. We got here, based on everything we're doing, potential energy at the top equals kinetic energy at the bottom plus the energy lost to thermal and sound. So what you can say here, okay, so this thing is equal to 0.9 mgh. And this thing is equal to 0.1 mgh. Equal. Is you good with that? Does that make sense?
Wait, what part is equal to 0.1 mgh?
The kinetic energy. So,
Oh, okay.
So if I said, let's do one more thing here. Ke bottom plus T plus H. Hooray for us. We said, but we know what this left-hand side is. So I guess the point here that this is how I want to drive it home, is that, okay, my left-hand side is mgh. Great, we know that. How, but then to get this left-hand side has to be equal to the right-hand side. Go back, third grade, whatever, equal sign. So how do we make that happen given this information? Sorry, take that away. Don't do that because that's not given. This is given. The thermal energy plus the sound is equal to 90% of the potential energy. What's 90% of the potential energy? That it's 0.9 mgh. Yeah. How do we make these things equal? How do I make the left-hand side equal to the right-hand side? Well, this is literally the only thing you can write to make these things equal. Good for sure?
Yeah, that makes sense.
Okay, cool. Just real quick, factor out, right? Factor out MGH, the common factor. 0.1 plus 0.9 is 1. You have a 1 coefficient there. Okay, so then you get two equations from this. One of them is T plus S equals 0.9 mgh. Yeah. If they ask for that, but we don't care about that right now. The one you get is 0.1 mgh equals 1/2 mv squared. I've just taken this whole thing and written it as a normal equation. So then you should get, I'm going to cancel m's. I'm going to multiply both sides by 2. And that's what the velocity is. So they didn't give any numbers at all?
I was only given a mass, a height, and
so you were given a height.
Yeah.
Okay, so then you can plug in, I think you're good with that, but yeah, you can get a number here, right?
Yeah, okay.
And so real quick here, this is your standard one, right? 2GH. Does that one look familiar?
Yeah.
Well, here you go. And I don't care if it's 50% of energy goes to the thermal. Well, you're going to have a different coefficient there, right? Same problem. It's just, this is the real key here. good on that?
Yeah.
Sure.
Yeah.
Cool. Yeah, I thought there was one on here that was like the kinetic energy of where's the baseball and the tennis ball? I swear we just did that yesterday. Oh, there it is. Okay.
Yeah.
That's a kind of a different one. But again, I don't care about them. Do you want to go through that one rather than another round of the worksheets 1, 2? We're doing
Sure.
pretty
If
good
we
on
could
time.
do like as many like different ones as possible, that would be great.
Awesome. Yeah, we're doing good on time here. So I have time to do just those 2 more math problems on that. I mean, maybe more time than that, but also this baseball one. Okay. Okay, so let's go back here and say, yeah, we talked about that. Oh yeah, we did do that one. Dropped in the apple. There's your equation as always. Okay, so I guess we can do a conversion if you really want to. I know you're really excited about conversions. I heard, so we'll do one. 220 feet. The total mass, passengers, and train is 3,500. Give you a little bit different here because I think you guys do this a little bit. Lose 100k joules to heat. Okay, what is the velocity? So looks complicated, but break it down as always. What are you given? What do they want? Before you do anything or freak yourself out at all, just that's where you start, always and forever. And so, okay, H 220 feet. I won't do conversion because I'm better than that. Just kidding. I'm going to use your thing here. I can write it for you. So what is it, meter? Yeah, feet per meter. How many meters per feet? Every 3.28. That's what it looks like. I think you're good with that. This is not meter down here. So then you get, 220 divided by 3.28. Don't forget your conversion. If they give you anything that's not meters, convert it to meters if you can. We're going to round it. I got 67 and a bunch of other numbers. That's the actual height. Make it very clear here. Great. And then what else? They give us the total mass of the thing. 35. I didn't put a unit, but it'll be kilograms. If it's not kilograms, convert it to kilograms. And heat plus sound, H plus S. I like thermal, which is heat, because I'm already using an H. 100 kg or kj, it just means kilo, just like kilograms. It's 1,000 grams or 1,000 joules. So 100 times 1,000 is 100,000 joules. Again, if it's not in joules, convert it to joules. Kilojoules doesn't work because if you put 100 into your calculator, you're not going to get the right answer because you need to put 100,000. The equation, as always, it's going to be like this. I would guess pretty much the whole time, unless he tries to trick you. Standard equation. I will say it over and over until you're annoyed at me. There is no kinetic energy here because it starts at rest. At the top, there's no potential energy at the bottom because they're asking at the bottom of the hill. There's no potential energy, mgh, h is 0. The thermal goes on the right-hand side of the equation. It is paired with the kinetic energy because if you haven't even started moving, how are you supposed to lose any thermal energy? I'm saying it can't be on the left side because you haven't done anything yet. You can't lose energy if you haven't done anything. So that's why it's at the bottom. So then you would do your normal equations, because what are we solving for? Velocity. I didn't write that down. We know that there's a v in here, which makes us happy. We know hopefully that's a number. So 1/2 mv squared plus t plus s, just the energy that's lost. And I can just solve for v here, which it would look like this. I'm going to subtract both sides. I'm trying to get rid of this thing. I'm adding it, so let's subtract it. That gets rid of it. What am I left with? 1/2 mv squared. If I am multiplying, I'm isolating v, so I want to get v by itself. If 1/2 m, which is m over 2, how do I do it? Well, let's multiply both sides by 2m, so that goes away. 2m, parentheses, be careful. It's not just 2m times that thing, it's the whole quantity, the entire left side, and then take the square root.
Mm-hmm.
Don't forget to subtract. And it's really just interpretation where you say, okay, I know that thing is 100,000. MGH, well, I don't know, it's 3,500. You do actually have to keep the mass here, notice, because you can't just cancel m's. So anyways, it's 3,500 times g, 9.8 times height, 67 meters, not 220, not the feet. Right. I would do it if I had more room, but I think even though it looks complicated, I think you're good on this, right?
Yeah, makes sense.
Okay. Are you sure? I can do it real quick on the next page, but if you want me to.
I think I'm good.
Okay. So the other one now that I reminded, which is a good one to do, and it's a good one to go over because it's the same equations, same exact equations, but it's the concept. And you're saying, how do I use the equations? Okay, how fast? Let's say, let me look at these equations so I can do something different. Okay, never mind. It has to be how fast. All right, how fast? Okay, would 175 gram baseball, it's probably heavier than that, have to be moving. So kind of cheating here, but I suppose that's why you're scheduled tutoring lesson. But the keywords here are the same kinetic energy. That gives you the equation you need. How fast would 175 kilogram base have to be moving to have the same kinetic energy as what? Well, something that has a mass and a velocity, right? We have to calculate that. Kinetic energy as a, I give it baseball. Let's do, basketball, and it's 2 kilograms. As a 2 kilogram basketball moving, it's a freaking Steph Curry pass. So this thing is like 40 meters per second. But so yeah, I'm gonna do what I want you to do, even if you understand it completely. This is what you do. This is what you do to solve it. You read, you can write down some stuff first. That's what I always say, but I would say first thing is mentally say, oh, I'm dealing with 2 objects, baseball, basketball, 2 different objects. Okay, great.
Mm-hmm.
Same kinetic energy. That's the first thing, really. So same kinetic energy. Okay, I get that. I'm an adult. I know what those words mean. It's the equation. What is the equation? It's same means equals. So all it's saying is the KE of a baseball, if it has the same kinetic energy of if they have the same kinetic energy, the kinetic energy of the baseball equals the kinetic energy of the basketball.
Mm-hmm.
And now that's the key here. That's it. And because the rest really is, okay, as always, what are the equations? Plug in the numbers. This is the concept. And then, as I said the other day. Okay, we got to be real careful here. Let's call, you know, M1 baseball, or as I said, BB, or you got to write it, I guess, because yeah, that's why they use tennis ball. And yes, notice this BB. Oh, that doesn't help me. Basketball, baseball. Be very careful. I don't care what it is. It's just so you know. I've converted immediately to kilograms. Let's write it out. I think you're Gucci on that. 175 kilograms. To go from grams to kilograms, divide by 1,000. And okay, M2 is another thing, or rather, they're asking, now we can say, oh, V1? I don't know. How fast would what? The baseball, which I've already said is number one. So they're asking for V1. This is all the
Mhm.
important stuff, because after this, then you plug it in. Okay, yeah, that's the most important thing. Figuring out where to start, and then your subscripts, and just taking your time and being careful if you feel a little not confident with it. So okay, if the first thing is the baseball, the second thing is the basketball. So that's 2 kg. We know how fast it's moving, 40 meters per
Mhm.
second. That's important stuff. Plug-in stuff. Be careful. M1 baseball is number one. Okay, sweet. I know the equation for kinetic energy. Let's add subscripts. I know the equation for kinetic energy. Let's add subscripts on the right-hand side. And that is, you can go here. We want V1, so let's say V1 squared. I'm going to divide both sides by M1. That means it goes away here, and I have M1 on the bottom here. And then I want square roots, as always. And then plug in the numbers. I know I seem, maybe I went a little fast on the whole equation and stuff, but to me, it seems like I'm confident that you're confident in what you know, and your algebra is really good now with this stuff. So the most important thing is these concepts.
Mhm. Yeah.
If you want another one just like this, where I go slower, was that too fast? Tell me what you want.
I think that made sense. I understand.
Awesome. That's good. I think you're going to do great, because you've been doing well, and it seems like you understand everything here. So
Yeah.
another type of thing, unless you have something or want me to cover these notes.
Um, if we could go over them, that would be great. Like just what you think are like some of the most important parts.
Okay. That first sentence on 216, law of conservation of energy. So let me give you some more insight, or let me try, and let me focus here. So law of conservation of energy, that's that equal sign, PE. That first sentence on that first page that says your notes, law of conservation of energy, that in words, energy cannot be created or destroyed, only converted from one form to another, yada, yada, yada. Okay, great. What is that? I don't, cool concept. But then why do I fail physics? Because those words mean that's what this equation is. That's literally what this equation is saying. Look, I have this energy, mgh. If I have a mass and I have a height, okay, I have some energy. More importantly, I have some potential to do energy, or the potential to do work, all the same thing, but you may not need all that. But the point is, I can convert that into kinetic energy. That's what you've been doing for the past month in all of these problems. This thing starts at rest. It's not moving, but all of a sudden it's moving. Why? Because energy is conserved. I start here at a height, and there's a force, there's a gravity working on it, a potential to do work. That's what it means, potential energy. And guess what? The energy associated with this height, it is converted purely into motion by the bottom here, by the kinetic energy. Now, this thing also means, this first sentence here also means you might say, well, what happens here? It doesn't seem like it's conserved if it's heat. What if there's heat, and what if I have air resistance? Well, energy is not conserved. And what we've done even tonight and last night is that, well, no, it is conserved. Let me break it down as simple as possible. The left-hand side of this equation equals the right-hand side. That's what that percentage means, that we worked on. 90% goes here. No, it just means it doesn't all go to kinetic energy. It goes to a different type of energy, heat and sound, or, you'll never see this, but nuclear, whatever, like it can go to anything. But it's that once you find a number, in other words, once you find a number, that number will never, ever change. If it's 100 joules, it'll be 100 joules throughout the whole problem forever. If it's whatever number it is, applies to the entire universe. Cool. No limit on how many times. Oh yeah, that's a good point. So you could go up here. You could go down here. You got to there has to be some force. There always has to be some force. Newton's laws still apply. They don't go away. But if you start here and then you convert it to motion, you could go back up. And guess what? You'd still have 100 joules, if you were able to get it up without losing energy to friction or thermal, whatever, sound, air resistance. Yeah. The tallest hill on a roller coaster is the very first one. Yeah, so the application of those problems, you're mostly going to only have potential energy at the beginning of your thing. So you only have to say left-hand side of the equation, mgh. Oh, that's not, I don't want to say anything else because you haven't seen that. But yeah, okay. A rock possesses 800 joules of gravitational energy dropped from the cliff. 800, there it is. 800 joules of work has been done. Remember, we were talking about this a little bit, I think. Work is joules, force times displacement. If I exert a force and it moves, I've done work. But joules, it's the same units here. I think we actually talked about mgh. Guess what? A force, mg, over displacement. Oh, this is something I definitely want to cover, actually. Okay, what do we got? This is good for you. Also, there was that one thing, just this is not related, but this is really important. If velocity or speed, whatever you want to call it, doesn't matter, because, okay, if speed doubles, what happens to ke? And maybe you memorize the answer as quadruples, but it's important to know why, because ke equals 1/2 mv squared. So if I double the speed where v, primed or whatever equals 2v, because I doubled the speed, we'll plug it in. Then the new kinetic energy primed equals 1/2 m. Well, you better just plug that in. Guess what? 2 squared is 4. So you get 1/2 mv, but times 4. Squared times 4. That's why it quadruples. So that might be a qualitative thing on there. And he might ask you to show it. I don't know. But then also I'm looking at this thing, the height. You may want to know, let me slow down and go back. So conservation of energy, everything we're talking about, all the problems we've been doing. If I have 100 joules of potential energy at the top of a hill, top of a cliff, I don't care, top of something, potential energy at the top. I don't care if we have thermal and sound, it's always going to, the sum of the kinetic energy plus the thermal is always going to be 100. And so then I see this thing, if you're halfway down, right? This is good. So what if I'm here, right? Let me go over here. What if I'm there? And you say, oh, I'm halfway down the cliff. I'll give you some numbers. It doesn't matter, but I'll give you some numbers. That 100 meters at the top. So now this thing is 50 meters. You say, oh, interesting. But it's moving, obviously, because it's been dropped. It's already traveled 50 meters. It's not like it's just, unless you stop the motion. But the point is, at every single point here, but any point there, it's 100 joules. The equation just looks a little different. It's just now potential energy. Why? Because it's mg times 50, not 100, plus whatever kinetic energy it has, because now it's moving. 100 joules here, 100 joules there, 100 joules there, 100 joules there, 100 joules here, everywhere. That's the whole point of everything you're doing, honestly. We got a couple minutes, but if you want to if you're ready to stop, that's good for me, but we got a couple minutes if you want them.
Sure.
Okay, cool. Sorry, it seemed like you were getting a little tired phasing out. So let's see, rubber balls dropped, bounces lower height. There you go. Oh, there you go. Yeah. So you can actually do this if you have a ball, tennis ball, anything, racquetball, even like something weird will bounce, like something that you wouldn't think of bounce, like drop a chair, it'll bounce a little bit, not very high, but bounce the ball and it doesn't go up as high. And you say, well, what happened to conservation of energy? Why isn't this working? Why doesn't my physics class, why isn't this real? Like, because if you slow down and think about it and you say, okay, I'm going to hold a ball out and I'm going to drop it. I'm going to hold a ball at some height. There's your height. And I'm going to drop it. Well, at the bottom of the ground, it's not going to have any potential energy because it's on the ground. It's going to be having kinetic energy. And based on what I just told you and what you've been learning, it's 100 joules the whole time, 100 joules the whole time, 100 joules. There's no energy loss. But this is a real life situation. Drop the ball, it hits the ground. It doesn't come back all the way. That's what we've been saying. That's what you've been learning. Well, 100 joules means, well, it better go exactly to where it was or else H will be smaller. And that's what, when it hits the ground, it loses a little bit to friction. The law applies. Energy of the system, which is the ball and the room or the floor, whatever, just the ball and the floor really. But then it's the air. You lost a little bit of energy to the air, that friction of the air molecules, which sounds kind of goofy, but that you can literally calculate that. And engineers go in and you can see that the molecules literally hit the ball and these tiny little air molecules literally slow it down. Obviously not very much, but there's a ton of air molecules and over enough time, it works. So that's why that doesn't work. And that's the example on your thing there. And he's calling it elastic. Again, I don't care. Heat, sound, elastic. But all these forms of energy better add up to be the same.
Okay.
Oh, I forgot about the weather and climate. Sorry. That was the most recent stuff too. Do you want to I can give you like 5 minutes on it if you want it. The weather and climate stuff.
Yes, please.
Okay. Sorry for that. Okay. Hopefully this is fairly straightforward, like just the basic definitions, the difference between weather and climate. Like, I guess I'll just talk. The weather is like, oh, it's 70 degrees right now. It's windy. Oh, okay, next week it's going to rain. Weather is short term. It doesn't matter. Like, and it's about a single place. Like, oh, over by your house, it's sunny. Over by my house, it's rainy. Over by the U of A, it's whatever, dusty. I don't know. But like the point is that climate is not that. It's averaged out. We're talking years, decades typically, and even some people do hundreds of years, but decades is the idea. And it's not just, oh, Tucson. Tucson where is it? It's part of Arizona, yeah, but it's part of the Sonoran Desert, and that's a climate. That's this whole complex system, and it's not like, because as you know, it could be 70 degrees here, but then out in Marana, it's usually colder, right? So that's kind of how you think about it and compare. And that's a good example. We live in Tucson, which, sorry, what?
Oh, I was just saying that makes sense.
Okay, yeah, cool. We live in Tucson, which is dry and hot, which is a climate really, especially because the weather is like, oh, it's hot. Well, it doesn't mean anything. It's 90 degrees, think of that too also. You got troposphere, makes sense. There's these layers of the atmosphere. There's actually some really good pictures. Just Google layers of the Earth's atmosphere. It's pretty cool. You got the stratosphere, troposphere, mesosphere, I believe, thermosphere, and then the exosphere, I think. But troposphere is where most of the energy happens, and the stratosphere, that's where all the clouds are. Oh, that's right, troposphere. Okay, troposphere, then stratosphere. Most of the weather happens in the troposphere. In the climate, right? Everything we understand about weather and climate happens in this bottom layer of the atmosphere. I was just doing this with my cousin, actually. Yeah, different pressures and temperatures. Like wind is just a pressure. Like it's a higher pressure over here than it is over here, or whatever, these 2 points. And so a difference in pressure creates wind. That's typically weather. You got a thing, climate, the generally prevailing weather conditions of a geographic region. Yes, geographic region, not just a city or a block, and over time as well, usually. Yeah, there you go. Throughout the year, averaged over a series of years. So I think, yeah, you probably got that. Latitude, latitude. When you think you're a sphere, use that, whatever it's called. That wordplay, the lines that don't go up and down from north to south, right? That's longitude and then latitude.
Mhm.
I guess it's more complicated than that, which is good to know in high school. But affect the climate,
Yeah.
most prevailing wind direction predicting. Yeah. So I think that's, yeah, the closer you are to the ocean, the more affected you are, the more climate is affected, right? And it's more humid, maybe colder, depends. Yeah, I think the big thing here is the difference between weather and climate. And he might give you 1 or 2 questions on that. And remember, troposphere, lowest layer, and all the weather happens there. All right, good luck. And yeah, I guess I'll talk to you soon, next week maybe. You feeling good about it?
Yeah.
Okay, good.
Yes. Thank you so much.
Of course, no problem. I'll see you.